Hello, welcome back to our channel, and we are going to talk about the design of analog circuits in today's session. And as you can see, we are using the SPICE circuit simulator to simulate the circuit. So before I get you into the details of circuit design, and we are going to use the technology model for the devices we are using. So before I take you further, let me introduce to you the basics about what this circuit is and how we can simulate it and understand the performance. Mainly, we would talk about the device models and the device parameters. So we will use the technology file to simulate our circuit using the devices that has the SPICE parameters. So here you can see I have used PMOS transistor here, and here also the PMOS, here also the PMOS, and here is an NMOS transistor. So if you closely observe, each of these transistors have four terminals. So that is your source terminal, this is your drain terminal. Let me in fact write them. So here is the source pin, drain pin, and that's your gate pin of the PMOS. Here also the gate pin, your source pin, and the drain pin of the PMOS. Same goes here. You have a source pin, you have a drain pin, and this is your gate pin. Only for the NMOS, we have got the drain pin here, the gate pin, and the source pin. So as I said, this is a four-terminal monolithic transistor. In the SPICE library of this circuit simulator, you have an option of choosing the monolithic transistor. So it means it's made from a single piece of silicon. And there is therefore the fourth terminal that is called as body or the substrate. So body of the uh, transistor PMOS here. This is the fourth pin, that is the body. Again, here is the fourth pin, that is the body. Here is the fourth pin, that is the body. So instead of writing the body here, I would use the word, let me define here. I would write here the N-type body. So that is for the PMOS. Here also N-type body, because for PMOS transistors are manufactured in the N-type of substrate. Here also the N-type of body, and here you have the P-type body. So the substrate in which the NMOS are fabricated is P-type substrate. Substrate in which PMOS are fabricated, that's NMOS actually. So if you look at the cross section of the NMOS and the PMOS transistors, we have explained that in some of the modules. So we'll not talk about that in detail right now. So just remember. So now each of these have 4-pin devices, and look at the connections, how we do it. So connections is the source is tied to of this PMOS M3 to the highest potential in the circuit, that is a VDD. And VDD we are using here about 5 volt, for example. We'll explain that. Then for the PMOS here, also the source pin is tied to the highest potential here, right? And then so body, which is the N substrate or N well of the PMOS here, is tied to the source, and not, we can also connect it to the VDD, that is the highest potential into the circuit. Okay. Now look at these connections here. So here is the here is also connected to the source, and the source is tied to the highest potential VDD. But for the NMOS here, the body is tied to the source, which is the source is tied to the ground potential. So we can say that the body of NMOS is tied to the lowest potential into the circuit, that is ground. Now, M1 and M2 are the main transistor. We would say M1 is an amplifying device. On the gate pin of the M1, we are going to apply the input voltage V in, and the output is taken from the common drain pins of M1 and M2. So from the drain pins of it, and here also the drain pin. However, you see that this transistor, that is M2, acts as an active load for M1. So there is a diode connected load, there is an active load, or in the simplest form, you can use a resistive load for the NMOS circuit. So you have V in here and you have this resistive load. So this resistor can be replaced by a diode connected MOSFET or the active load, which is shown. Active load in the sense you have to provide the voltage at the gate pin of this transistor and where that voltage is coming. So what we are doing here is you are using M3 actually and M3 actually to mirror the current in M3 into the M2. Okay, so and by that we are also providing the bias at the gates of the M2, and this bias voltage is called as VB. So if you see that in our previous section module, we have explained this circuit where, let me draw this circuit for the clarity. So here is our circuit where you can actually see we are using this PMOS. This is your M3, this is your M2, this is tied to VDD, and this is also tied to VDD. I'm just redrawing this circuit again. And here you have the PMOS again. Here the gate is tied to the drain. Here the gate is tied to the drain, and this is your ground. And now this transistor is like, okay, not here. This is not the case here. So let me correct that. Well, so you have this connection. However, right here you have got this kind of things. So this is the circuit and here is your output. So this is basically your M1, this is your M2, this is your M4, and this is your M3. So same circuit. This is the circuit we are drawing. So this is an active load here, active load of the M1. This is an amplifying unit, amplifying unit. So this is basically, so it will provide the transconductance GM multiplied by the output resistance offered by the M2, that is the RDS, would be the output voltage, and it will be inverting in more nature because that's the inverting amplifier. So we'll see that this is our theoretical expression. So from the small signal model, we will arrive at this expression actually. And in fact, this RDS is the parallel combination of RDS1 in parallel with RDS2 from the small signal model of this circuit, which we have explained in our previous module. So do refer to that if you want to understand how we arrived at the output expression. So we can also calculate, this is output divided by input. This is the gain. Okay, and for gain, right. So you can see that the link is in the description of this module. So coming back to our circuit right here, we are talking about this circuit, which we have used the SPICE to take the devices from the SPICE library, and we have accordingly connected all those together. So what we have done, let me explain you also how I use the SPICE simulator for the interconnection and the selection of the components and all those things. So let me just get you here. So as you can see, what I have done here is, this is very important to understand because we are using the real circuit design and we are doing the real parameters we are using. So first thing, when I open the net schematic, it was a blank schematic. Let me clear this drawing here. And with this blank schematic, I use this component library here where I can type PMOS or I can type NMOS. With that type, you see that there is this N-channel MOS transistor. So this is basically its body right here is tied to the uh, the source pin of this transistor. For the PMOS, if we see that, where is the PMOS here? Here. So here also the body is tied to its source pin, right? But there are other transistors, that is NMOS4 here, NMOS4, and then there is this PMOS4. So the difference is in the direction of the arrow. For NMOS, the direction is inward. So it says it is an N-channel MOSFET transistor with explicit substrate connection used for monolithic MOSFET. So this explicit substrate is not connected in this transistor. So you have an option of tying it to the highest potential in the case of PMOS and tying it to the lowest potential in the circuit in the case of NMOS, which is ground. Okay, so I have chosen NMOS right here, and I put it those transistor here. Then I clicked here again, and then I chose this PMOS 4. I clicked it, and with that I got all these transistors in the fashion I have shown right over here. And you see that this is written PMOS, here it is written NMOS, PMOS, PMOS, and these transistors. So coming back to our circuit here, so I have, therefore I've got M1, I've got M2, I've got M3, and I've got M4. Now, what I did once I put them together, so like I said, M3 and M2, they are acting as a PMOS current mirror together. So current in M3 is mirrored into M2. So that's how the things work. Depends on the W by L ratio. We can choose the magnitude of the current that will be mirrored in M2, right? So we'll see that. So now M3 and M4, you see the gate is tied to the drain. Here also gate is tied to the drain. So that makes these transistors always operate in the saturation mode. They will always be remain saturated, and body connections I have explained earlier. However, there is a bias coming on the gate of the M2, and that will decide how we do that, right? So how much current will be mirrored from M3 to M2, that we have to decide. Okay, now there is this thing, I have used this VDD of 5 volt. I can change the voltage here also, and then on the V in, I am using the bias voltage about, let me just remove it for a moment, DC value of 2.5 volt. Why I chose 2.5 volt, will explain that as we progress through this discussion. Now, what is this L and W, which has been highlighted for M1, and what is this .inc include? There is some file, so that file is a model file, okay, and then there is the .op, which is a simulation command. We will run the operating point analysis and accordingly. So theoretically I have explained that this is a common source amplifier where M1 is the amplifying device and R2 M2 acts as an active load. The output voltage divided by the input voltage is GM times RDS, which is the drain to source resistance of the transistors. Okay. Now we want to simulate and analyze the performance of this circuit using some technology file. So we are doing the real world design. So for example, nowadays advanced analog designs are designed using sub 100 nanometer technologies, which stands for 65 nanometer, 90 nanometer, even up to 22 nanometer. So it means the smallest possible transistors have a L channel length of 22 nanometer. So that process node is called as 22 nanometer. If it is process node or called technology called as 45 nanometer, it means the smallest transistor available in that transistor in this technology is 45 nanometer. Okay, so let me highlight these voltage sources. So if I click here, so you see that the VDD shows where my VDD connection is coming here. So I right click here and I choose click here, highlight net. Okay, I right click here, you see that I click here, then V in, it will show me where the V in is going right here. Okay, now if I right click on the VB and say highlight it, so it shows me where the VB is reaching. Okay, so it is reaching to the gates of M3 and M2, and to the body of M4 is reaching to the VB actually. So not to the VDD, but still close to VDD, which is VB. Now we have to simulate actually what would be the drain current in M3 and M4, and then we will see, okay, what would be the drain current that will be mirrored in M2 then. So for that, we actually can use this file. So let me do that. So what I have done here, so when you actually select these components in the another window, so right click here. So after you right click, you actually can, this is now very important point that we have to explain. So here you see there is a model name NMOS, which is here. Then you have to input the length of the transistor, the width of the transistor. I just explained to you. The length is the smallest channel length in a technology available. So if it is 22 nanometer, you write that. If it is 100 nanometer, write that. It is more than for example, it is 180 nanometer, write that. Okay, now then there is other spice parameters such as drain area, source area, drain perimeters, source perimeters, number of parallel devices. So how many, if you write let's say 10 here, so there are 10, look, m equal to 10 come here. So if you write here 180 nano, so that will come here. It's all things are coming here. If you write like 500 nano, so that will come here. Okay, so this is how I define the parameter. But what about this AD, AS, PD, PS? Where to get these parameters? And just like I mentioned, number of parallel devices, it means how many devices you want to be connected in parallel. So it means if you connect like of this dimension devices, single unit has 180 nanometer, W is 500 nanometer, and if you have a 10 devices in parallel, such that if you just write 10, so it means this single device has effective length of they are in parallel. Okay, so their width would be 500 nanometer multiplied by 10. So it would be like 5000 nanometer, which is 5 micrometer for the given channel length. So that it means. Now the question is where to get the values for AD, AS, PD, and PS. So answer is we have to use the SPICE card or SPICE model file for the MOSFETs, NMOS and PMOS both, which is provided by the manufacturer actually in the commercial aspect. But for the open source, you can also have it, which is the topic of today's discussion. We are going to use the free available model file, which is not exactly the commercial one, which is provided by the vendors, but by using that, you can get a feel about how your real world circuit will work and how it will perform in the real world. So the model files we are going to use is the BSIM, which is developed by the Berkeley group with the University of California. It's an open source model. So what I have done to get all these parameters, similarly, I have done this for the PMOS, so you can see that. Okay, I will do it for PMOS. So this I have done in my circuit, which is actually shown right over here. Okay, so this is shown right here, and we have done that. So now L equal to 180 nanometer, W equal to 900 nanometer. So I have chosen this like right here after right clicking it. So you see that I have just put in the values of L and W for NMOS. Then right clicking here, I have chosen 180 and 1800 here. So I have chosen the W of PMOS to be twice to the W of NMOS. So remember, W of NMOS is 900 nano, lengths are same. So why is this? Because the mobility of charge carriers in NMOS, which are electrons, are twice to that of mobility of charge carriers, which are holes in PMOS. In other words, PMOS mobility charge carriers, that is holes, is half the charge to that of charge carriers of NMOS. So that's why you have to have an equal current in the both the transistors. You have to choose width to be twice, at least twice, to that of the M1, so that the same current will flow. Okay. So similarly, I have chosen the length same and the width is 1800 nanometers. So obviously widths of M3 and M2 are same. So I can write the expression here, the output current that will be mirrored actually in the M2 and M3. So let's say here I will call it as a reference current, and here the current through M3 I will call it as a I out, which will be mirrored. So I can write the expression I out will be um, uh, W by L of M3 divided by W by L of M2 multiplied by I reference. So that's the equation when you design the current mirror circuit. So this is the PMOS current mirror circuit. So obviously W by L of M3 and M2 are same. So my I out will be equal to I reference. Okay. So that's how it is. Now you see the PMOS, actually PMOS also, let me give you the understanding about what would be the ratio here. W by L ratio again 10. So you see the W by L ratio here is 10. In the case of PNMOS, the W by L ratio is actually 5. So 900 divided by 180 nanometer. Okay. So what is happening here, W by L ratio here and here, that's the same. So if I apply 5 volt as a VDD here, so the same current will flow, and therefore the voltage, that's the VGS of this transistor will be equal to the VGS of this transistor. Right, that is, so 2.5 volt here will be there. So it's just like a voltage divider, this together as acting M3 and M4 for the same current flow, and same current is flowing because they have the same W by L ratio, and their gates are connected to the drains. Here also gate is connected to the drain. Okay, so now 2.5 will come here. So VB will be at 2.5 volt, which is a bias voltage to this transistor M2. Okay, so now why is this only L and W of M1 is highlighted on the screen? Why not for M2, M3, M4? That I have done. So what I will do is I can press the control button on the keypad on the computer or laptop keyboard, and then right click on M2. So with this, it opens the component attribute editor, and with that you see for value 2 in the attribute where L and W's are mentioned. So I can double click here, and this is the attribute to appear on the netlist line. So if I double click here, originally it wasn't a cross there, but if I double click here, then there'll be a cross. So let me double click, it disappears. If I click OK, and this line is disappeared now. Again, I can show it for M2. For example, I press Control on the keyboard and then right click this transistor, and look, this value 2, now there is nothing here. But if I click right here, so this is the attribute now will appear on the netlist line. So if I click here, so this has appeared here. So let me use the drag, which is F8, and maybe where I want to place it somewhere here. Okay, somewhere here. So that is how is done. Okay. So first thing first, we want to make sure, as I said, M3 and M4 will operate in the saturation region because of their connection between drain and gate. They are like diode connected transistor. I want to ensure the M2 is operated in the saturation region and M1 is also operated in the saturation region. Why? Because in the saturation region, their output resistance will be very high, ideally infinite. But we are using a short channel transistors, there'll be some finite value of output resistance, which is indicated by or modeled by a channel modulation effect, channel length modulation effect lambda. So this effect has been taken into account in the SPICE model card that we are going to use for this transistor. Because remember, if you simply right click it, all these parameters, and there are hundreds of parameters, only 7 or 8 parameters are mentioned here. So depends on the how advanced model you want to use. For level 1 model, a level 2 model, and level 3 model, there would be a SPICE parameters with each MOSFET up to 10, 20, and up to 50 respectively for level 1, level 2, and level 3. But nowadays we are using a short channel technology and a BSIM4, which is advanced model up to level 49, level 44. So we just simply say BSIM4 is the latest and the most advanced available to date. So that model, that SPICE card will have hundreds of parameters, as we are going to see. And we are going to use that advanced and the latest technology model because it will have the more closed or most close behavior of the devices we are using, that is PMOS and NMOS, and therefore our circuit simulation because of that is likely to be accurate when we actually in the real world will fabricate such circuit. Okay, so as I said, the gate potential on the M2 should be such that you want MT to be also operated in the saturation mode. So in order for M2 and M1 to be operated in the saturation voltages, their VDS has to be greater than equal to VGS minus VTH. Okay, so what it means, the voltage across drain and the source right here, like I said, right here is your drain pin, here is your source pin. So this VDS drop has to be minimum, or let's say VD sat has to be greater than VGS, that is this voltage between gate and the source here, minus the threshold voltage or turn on voltage of the transistor. So let's say if I have 2.5 volts here and VTH is 1 volt, so here the drop is 1.5 volts. So this voltage across drain and source has to be greater than equal to 1.5 volt. Similarly, for the PMOS, you have VDS, which is your source and drain voltage. So obviously a source is connected to VDD, for example 5 volts here, and then you have this is 5 volt here, and the VB, like I said, 2.5 here. So your VGS is minus 2.5, and if the threshold voltage is minus 1, so the drop here is minus 1.5 volt. VGS minus VT will be minus 1.5 volt, and then your VDS, that is this drop, has to be greater than minus 1.5 volts. So it should be, let's say, minus 1.6 onwards. Okay, that's the negative voltage polarity. But then only you will say M2 and M1 will be saturated, and that's the condition for maximum gain offered by the circuit. Okay, so how to identify and how to use that in doing that? We can do the hand calculations and see that our simulation results are in uh, close match with the hand calculation when the circuit uses a long channel MOSFET. But with the advanced technology using the short channel MOSFET, such matching is difficult or challenging because there are many effects such as channel length modulation, body effect, and all those things take into consideration. Okay, so what we'll do, we'll just focus on approximation of your analysis, and we'll understand how the circuit works. We already know what would be the gain, we already know the current mirror action, and we already know the condition for making the transistors works. Okay, so this is the condition we have to understand, and we'll compare the VDS of each devices, whether that is greater than or equal to VGS minus VTH. But where is the VTH value? That is available in the SPICE model. And where is the SPICE model? Example here, learning microelectronics. So I can use the BC model or any other. So here you see that the model files are available, 0.8 micron, 0.35, 0.18. So for example, if I click here, then it helps me to download. So in one of the folder, I have downloaded this model. This is the zip file actually. So I downloaded all these model files, for example, 180 nanometer technology, 350 nanometer, just to 45 nanometer and so on. So I just show you. And after downloading, I open that and you see now here in this particular folder, I have got these two. And then I right click on all those models and then I extracted. I just chose extract all. With that, I got these three folders, P18, P35, and P45. So for example, if I click here, so I have got this P model card. So, okay, so I double click here and open it. And this is actually your, let me clear the drawing so you better can see it. Now you can see that this is your spice model and this is your actually level 49 model. So like I said, there is a level 1, level 2 up to level 49. So it's a BC model, the most advanced, one of the most advanced for the 180 nanometer technology. It means the channel length is 180 nanometer. Okay, so let us try to just understand what these parameters here are. So the spice deck or spice card starts with such syntax which states dot model and MOS is the model name is the and it's the type of transistor. Second is the NMOS again. It can be a small letters also. So, but then again, if it is so, you have to change your schematic labeling in the transistors. Okay, remember we have the transistors which are named with capital CMOS, but if in the spice deck there is a small case letters used, so right click here and type the small case letter, otherwise your circuit won't work. So coming back here, we are using the spice card for the NMOS, which has hundreds of parameters as you can see. So what parameters? This is level 49 and this is 3.1 version. You can use any other version. So T norm is the nominal temperature. It will provide the simulation results for the device and the circuit at room temperature 27 degrees Celsius. T ox is the oxide thickness. In this comma, there is like proc delta something written. I'm not sure what that is, and we are likely to have error because of that. Or spice circuit simulator will ignore those parameters and give us the results for the remaining one. This is NCH, still not, but look at here, VTHO, that is the zero gate bias threshold voltage, which is 0.36 volts plus VT shift. There is something has been taken into account, but we'll just focus on 0.36. Now K1, K1, K2, right here, and K3. These are the parameters related to the process, which can help us to give us the transconductance of the device. Then you have like, and there are so many other parameters which we can just search on the internet and get the information about that. But that's it. Now you can see that from these parameters, you can extract the mobility of the charged carrier for NMOS and the mobility of charged carriers, which are electrons in NMOS. You can get the Cox, value of Cox, which is basically epsilon ox divided by Tox. So that's the oxide permittivity divided by the oxide thickness and so many. And now look, if you scroll down, you have got the model for the PMOS, similar one, except the syntax. You have PMOS here 2 times. That's the model name and the model type. Version 3.1, level 49. Room temperature is 27 degrees centigrade. Tox is given. VTH here is minus 0.39. Okay, so you see now the VTH is pretty low, just about 3.9 volts to PMOS and 3.6 to NMOS. So it's just like we need a VGS little bit greater than the VTH, okay, to make the transistor turn on. So that's it, and we are going to use this model file into our library. Now look at this route. So what is the route or the library in which this model card is stored? That is D drive, and this is the folders, and that's the route. So what I have done here is copy this, and then I can just remember this. This is the route and this is the name of the model card. So you can do one thing. You just click this .op here, which is spice directory, and then in the spice directory, click here and Control V. I have copied it, and now with Control V, which is paste, I have got the name of the library, and then I will put write the command .inc, actually .inc here, space, that's the name of the library, and then slash and the name of the file actually. So what's the name of the file here? You can see that here, P18 underscore model underscore card. So I will just do that. Oh, well, actually I have done that. So I will write that. That is, and once I write that, just click OK, and you actually can see now I have used this .inc d. This is the folder name, and this is the model card. So this is the command. If you right click here, you have got this one, right? So this is spice.lib directive, and you must include that. Once you do that, click OK. That's it. Now you see, now I have got the circuit ready, all the interconnections. I have used the 2.5 volts here and the 5 volt here, right here. But do I need a 5 volt supply to be used with 180 nanometer technology? No, really no. So what I am going to do here is for 180 nanometer, I have a supply voltage of 1.8 volt maximum, if I remember correctly, 1.8 volts. So that's how it comes. And then here I would use the 0.9 volt. So remember, threshold voltage of NMOS is just 3.6 volt, so 360 millivolt. So 0.9 volt, which is 900 millivolt, is greater than. So here we can write, now in this case of the transistor, we have got VGS is greater than VTH. Okay, so let me write that here. So VGS greater than VTH. Okay, here also you have now 1.8 volts here, and the threshold here is 0.39 volts, and the voltage here will come, like I said, because they are acting as a voltage divider. The voltage here will be 0.9, okay, half of it. So here 0.9, and then 0.9 minus 1 point. So here the drop here is minus 0.98 volts. So again, it is greater than this volt, right? That's the one. So here also we'll say that VGS is greater than VTHP. Here VTHN. Okay, so just see the magnitude here. We are taking the magnitude actually, or maybe just yeah, yeah. So if we take the magnitude, then the negative signs can be ignored. Okay, and then with that, we want to understand what is the GM, that is the small signal transconductance, which is actually mu n C ox W by L into VGS minus VTH. This is for the device transconductance. Transconductance. That's the formula. So We don't know how to calculate mu n and then Cox, W by L, no, L we know, VGS minus VT we know. So GM, if we know, then obviously like in the very beginning we have got, and we want to determine this one. So which is GM times RO, and RO is RO1 in parallel with RO2, and that's the RO2 here. That's the output resistance of this transistor, and RO1 output resistance of this transistor, and that's your gain. Okay, again, because of taking magnitude, we don't have to add the minus sign here. And the ID in the saturation region is mu n C ox by 2 W by L. This is applied to NMOS and PMOS both, okay? VGS minus VTH whole square. Okay, so we don't know these parameters actually. We don't know the transconductance actually, but we can actually calculate mu n and Cox. We'll see if the spice parameter gives us that value when we simulate the circuit, right? It should give us, right? Okay, we'll see that, and then we'll calculate, and then we'll compare our theory equation with the simulation results if that is possible. So I think I have given you enough information about how we are designing the circuit of common source amplifier with biasing. This is a bias network for the common source amplifier, and we are designing a common source amplifier using 180 nanometer technology. Supply voltage is 1.8 volt. So let us see the node voltages after we run the .op simulation, which is the operating point analysis using SPICE. How we do that? So for doing that, we just click simulate, click control panel, not the control panel, click simulate again, click edit simulation command. With that, let me remove this right over here. Okay, and now what we are doing here is DC operating point. So I will write .op here, which I have done. Then click OK. So .op has appeared here. Okay, .op has appeared. Now all set, right? So we want to understand what are the device currents and the voltages across all pins like VDD, VB, voltage drop across each transistors, and to make sure whether all of them are operating in saturation region or not, because that's we want. So click simulation, and here we are. Here we are. So what you see here, let me erase this also, so better we can see. Let the formula be there. So now what we see here from the first, VDD is 1.8 volt. Is that the case? Yes, it is the case. We have VDD equal to 1.8 volt. That's the power supply used in our circuit. Vin is biased, which is 0.9 volt here, of course. Now look at the output voltage is 0.16. So it's like 160 millivolt. Well, 160 millivolt. And if the M1 has to be saturated, then VGS minus VTH, which is the overdrive voltage, should be less than this 160 millivolts. So VGS is 0.9, VTH is 0.36. So like it's like 0.9 minus 0.36 is about 600 something. So obviously your output voltage is just 160 millivolts. So obviously you don't really have this transistor operating in the saturation region, right? That's the clear. Now look at the VB, which is now 0.9 volt as theoretically calculated. Now the current in the, so obviously M1 is in linear region, right? Because VDS is less than VGS minus VT. Now M2, that's the current through the PMOS, this active load is minus 7.3, obviously minus sign there because it's PMOS. So it is 73 microampere, approximately 73 microampere. Then the base current, the body current and the gate current will neglect because they are negligible. And the source current obviously is the positive here. Now the drain current of M3, look at this, or rather we should drain current or source current, doesn't matter. So it's a drain current of M3, which is a PMOS, again negative, and it is 63 micron. So here is 73 micron, 63 micron. So approximately same, but still not same, because that's a current mirror. So we theoretically predicted M3 will mirror its current into M2 because it's a current mirror, right? But we'll investigate that in a moment. Now look at, come down, idea of M4. That is M4 obviously is gonna be same 63 micro, because M3 and M4 are connected in this fashion, the same current, because their W by L are same and their gate to source voltages are same. All right. So gate to source voltage here is 0.9, and here also gate to source voltage is 0.9. Is that so? Just a minute. Let me check. So we are done. We just said that the M3 and M4, they have equal VGS, that is minus 0.9. And now what is there? Look at the current through the M1, which is the drain current we are interested. Here it is. That is how much? 7.3, which is 73 micron. So obviously 73 micron, and here is 63 micron. That is because this guy is out of saturation, is in the linear region. Obviously the voltage drop across VDS here is less than VGS minus VTH. So what we'll do is, maybe we have to either decrease the voltage to the gate, and we'll see how it behaves. What about PMOS? The VB here is 0.9 volt, and VGS is minus 9 volt, 0.9 volt, not 0.98. It's a 0.9 volt, and that's the VTH is minus 3.9. So obviously there is like about 550 millivolt overdrive voltage, and your VDS should be greater than that. So VO is at 0.16, and the VDD is this one. So yeah, this guy is in saturation, but there is a large voltage drop across it, and these two are always in the saturation for sure, because the gates and drain are tied together. We'll check that. VB is 0.9, and this is ground. So your VGS minus VT. So because VTH is subtracted from the VGS, so VDS will be always greater than VGS minus VT. So here for M4, you have got like 0.9, and there, which is greater than about 550 millivolt. Here also you have got 0.9 right here, which is greater than 550 millivolts. So what we'll do one thing, we'll just change. Oh, look at this, something has come here. So before I explain you that, let me correct the biasing. So what we are going to do is right click here, and instead of 0.9, let me just, how about 0.6 volt should be okay. That's the bias point I'm doing, and correct the simulation again. And look at now if we succeed. So output voltage is now 1.7. Look, earlier it was like, oh, but it has got too close to VDD. So that's also not good. So let me choose again this voltage here, that is 0.9 earlier we chose. So maybe 0.8 should be, because we are keeping the W by L to be same, right? So we run the simulation. Look at this, VO is 0.5, reasonable. We 0.5, so I have to choose and bias each transistor in such a way that they all in saturation. So 1.8, 0.5, so voltage across this transistor M2 is 1.8 minus 0.5, which is about 1.75, Still a big drop, but still okay. How about this? It is 0.5, and this is now like V in is 0.8 minus threshold is 350 millivolts. So still this VO is like, oh, still not enough to make the M1 saturated, right? So what we'll do is we'll click here 0.8, so maybe 0.75 maybe should be okay, and we'll see how much is there. Now it is 1.14. Now seems reasonable. Okay, so 1.14 is the output voltage, which is the VDS of M1, and that should be more than 450 millivolt overdrive voltage. So it's saturated. What about this drop? So 1.8 minus 1.1, which is about 0.7. So 700 millivolt, and this drop overdrive of this is about 0.9 minus 400.5. So this seems to be saturated again. This is not seems, but it is saturated. We'll see that. Okay, and these two guys are sort of saturated. What about the currents? Now look at the level of the current. 6.0, that is 60 micron through M2, and M3 63 micron. So it's very close now, M3 and M2. 61 and 63. So you have to adjust W by L ratio or bias voltages, then maybe you can see that. What about ID1 61 and ID4 is 63. Okay, so with that said, look at this now. Once I close that, this window opens up. It is showing me some questionable use of curly braces in dot model. So this issue or warning is related to the model file we have used from the internet. So make sure the model file you will use is authentic enough. So here we see now there is this error coming here which says undefined symbol 4.1 prog delta, something like that. So where is that? We can read that model file again and do that, or we'll just remove that because it says that ignoring bsim parameter, ignoring bsim and all those things, that's not a concern. We'll see whether it gave us the result. But he says, it says now that direct Newton iteration for .op point succeeded. So just make sure that the model file you use is correct, authentic and free from errors. Then you will not have the errors that is shown up here. But from now, we will see all those parameters, M2, M3, M4, M1. So have a look at this M1 first, that is your amplifying device. So ID here is 60 micron. VGS here is about 75, 7.5 into it, 0.75, right? Is that what we used? Let me check here. Yeah, 0.75 volt we have used here, that's correct. And then VDS is 1.15. VBS, body voltage with respect to source, threshold is 460 millivolt. VDSAT is your VDSAT is voltage is like how much is 20 0.2 volt actually, right? Is it 0.2? Let me check here. Yeah, so see VDSAT is 200 millivolt. So at 200 millivolt extra, it got saturated. Okay, now you have GM, which is about 345 microamp per volt square. Then you have GDS, that is the output transconductance. Again, you have 11.5 micron per volt. GMB is the body related transconduction. Then you have capacitances, and then you have all these parameters. Will not use those. Similarly for M2, which is the active load. Look, ID is same as M2, M1. Then VGS is your VGS is like 900 millivolt. VDS is like 650 millivolt, and VDSAT is like 320 millivolt. So it is also saturated, right? Just a minus sign because it's a PMOS. Then its value about GM, GDS, GMB are given. Good. M3 and M4, they have like 64 micron current, so which is mirrored here in M2 and then M1. Pretty close, not exactly same, but still okay. 64 micron and 62 micron, fine. VGS here is 900. Then you have VDS is 900, and VDSAT threshold is 486 millivolt. VDSAT is good. So look, for all these transistor, VDSAT is about 320 millivolt. For this, it is 200 millivolt. So all are saturated. Good. All transistors are saturated. This circuit is perfect for simulation. So we have successfully completed the operating point analysis and the biasing of the transistors. Now from the simulation, we have got the value of GM. Did we note that? Did we note that? Let us note that the value of GM. So we'll not take into account these parameters. Rather, we close it, and what the values we get it from the spice. We'll note that. So we have to note the parameters here. Write down the VO divided by V in is what we want actually. So here VO divided by V in, which is GM1 times RO, and RO is in parallel with RO2. So one right here, which is RO, and which is we'll write GM1 divided by 1 by RO. Oh, no. I will not write GM divided by RO. Yeah, that's it. Here RO, and RO is actually 1 over GDS. Okay, so we'll put that value of this one. So GM can be calculated as GM1 is here, GM1, which is 345 into 10 to the power minus 6 microamp per volt square. Okay, sounds good, fine. And what about GDS1 and GDS2? So GDS1 is this, GDS2 is this. So GDS1 is 111.5 into 10 to the power minus 6. We should not do any mistakes. So 11.5 into 10 to the power 6, and GDS2 is equal to here 16.5 into 10 to the power minus 6, right? So that's how we have. Now RO1 would be 1 over GDS1, which is 1 divided by this value, that is 11.5 into 10 to the power minus 6, and RO2 will be 1 over GDS2 equal to 1 over 16.5 into 10 to the power minus 6. So once you have the values of R1, RO2, because you have the values of GDS1 and GDS2, get the value of RO, plug in that value RO here, you have the value of GM here, and give me the value of VO over V in. That is your theoretically calculated, or in fact the SPICE simulated gain, right? With the DC analysis, we have done that. Okay, so this is how you will do it. Okay,